Good evening, everyone. We'll be starting the session at 6:10. We'll wait if some more people are joining. Meanwhile, if you have any questions or any doubts regarding the last week lectures or any assignment questions, you can ask me or you can put that in chat. Okay, so we'll start the session now. Yeah. Good evening, everyone. Today we are going to discuss about the week 4 lectures of the course, that is Groundwater Engineering. Hello all, I am Balram Shah. I am the PMRF TA for this course. I am a PhD scholar at Interdisciplinary Center for Water Research at IISc Bangalore. So with this, we'll start the session. If you have any questions related to the previous lectures or any assignment questions, you can ask me. If not, maybe we'll start. Okay, so we'll first do one or two previous questions, maybe just to brush up. So the first question that we have is infiltration capacity of the soil depends upon. Your options are number of voids present in the soil, option B, shape and size of the soil particles, Option C is arrangement of the soil particles. Option D is all of the above. If anyone of you wants to say, or maybe in the chat box if you want to put, you can. These things we have studied earlier, right? In the last lectures or the last sessions. So we remember the infiltration capacity. What is infiltration? Is the process of water going vertically, or movement of the water going vertically from the soil surface to the subsurface layer, right? So infiltration capacity, what is infiltration capacity? That is the maximum infiltration rate that any soil layer can happen. So this maximum infiltration rate can be dependent on number of voids present in the soil, right? Because let's say if more number of voids are there, then infiltration will be easier, right? And hence infiltration capacity of that soil layer will be more. Yeah, option D will be correct. We'll just see all the options. Option B is shape and size of the particles. We know if, let's say, if the size of the particle is very slow, very less, let's say for example clay and all. So for clay and all, what will happen? The voids are very less, right? So because of this, the infiltration capacity of the clay particles will be less. Then arrangement of soil particles. Let's say if some soil particles are there and it is kept in, let's say, in this way, then you see the voids are more, right? Whereas if we can take some different shape and size and the arrangement will be something like this, then there is no voids again, right? Very less voids are there. So for this again, the infiltration capacity will be less. So the correct answer will be all of the above. Okay, so correct answer is B. Any question here? Okay, if not, we'll move to the next question. So the next question is an ideal fluid. Okay, so before that, maybe we will start then. I'll explain a little and then we'll move. Okay, so yeah, maybe we'll start with fluid. It's a simple term, but still it is an important term. Can you tell me what is fluid? We are studying groundwater engineering and we know water is a fluid. But just to be in the same line, I want to know whether you guys know what is fluid. What is fluid? Anyone? Okay. So what is fluid? We know that fluid is a substance which flows. We know that something which flows, we call that as fluid. However, this should have continuous deformation when exposed to a shear stress. So even if the shear stress is very minimal, eh, there will be a little deformation and there will be a continuous deformation. So uh, just not the substance which flows. So it is a fluid is a substance which flows with continuous deformation when exposed to any kind of shear stress. Okay, so now when we know that what is fluid, we'll now move to types of fluid flow. So here only in the last session we ended, right? What are the types of fluid flow? We have seen. First one is steady and unsteady flow. Okay, so here we should be little focused because even if these terms are easy and maybe one time you are seeing, but these types of fluid flow you will be seeing throughout the whole lectures, because assumptions on any of the law or any of the other equations that you will be seeing will be based on these kind of any of these kind of fluid flow. Okay, so we should understand each of the fluid flow properly. Okay, so what is steady flow or unsteady flow? So we know, first I'll discuss what is steady flow. So steady flow is the flow in which characteristics such as maybe velocity or something like that characteristics of fluid like velocity, then temperature, pressure, density, etc. If this do not change at a point with time, we call that flow as steady flow. So let's say if you are seeing a fluid, yeah, or maybe a section of the fluid, let's say we'll see the from the side view, let's say fluid is flowing in this direction. Okay, so fluid is flowing in this direction, maybe we'll see only till here. Okay, and maybe at we'll decide one point. So let's say if at this point the characteristics are not changing at any time, at any given time. So let's say if you see at 1th second and then 10th second, then maybe 1 minute, and then after 5 minutes also, if you see that at this point the characteristics like velocity, temperature, pressure, etc. do not change, then we call this flow as steady flow. Okay, so mathematically if we write this, how we will write? So let's say if we are talking about velocity, then change of velocity with respect to time will be 0, right? For any given point. So let's say if we are considering x naught, y naught, and z naught as a fixed point in the fluid. So let's say this point is x naught, y naught, and z naught. If we are considering this, then mathematically we can write del v del t as 0, because change in velocity with respect to time at any given point is 0. Similarly, other characteristics also we can write. Okay. So therefore, what will be unsteady flow? Unsteady flow will be in which these characteristics will change over time. Okay, so we can write del v del t won't be equals to 0, or let's say any other characteristics also, del p del t won't be equals to 0. If these characteristics are changing with time, then we call that as unsteady flow. Okay. Okay. So next we have uniform flow and non-uniform flow, right? So what is uniform flow? So let's say uniform flow is the flow in which these characteristics, or let's whatever you say, characteristics or properties of the fluid, like again velocity, pressure, temperature, etc., it changes with respect to time, but does not changes with respect to position. Okay, okay, there is a small correction here. So if we say changes with respect to time, then we are considering that this flow is a unsteady flow. Okay, so here we will only talk about what is uniform flow. So if there is any flow in which the fluid properties, for example, uh, like velocity, temperature, etc., does not change with respect to position, then we call that as uniform flow. Okay, so let's say if you are seeing in one dimension only, then you can write del v del s at any time, that is t equals to constant will be equals to 0. So if the fluid properties does not change with respect to position, then we call that as uniform flow. Otherwise, we call that as uniform flow. So for uniform flow, what will happen? The del v del s will be not equals to 0, right? Mathematically. Okay. Then what are the other types we have studied? We have also talked about compressible flow and incompressible flow. Okay, so what is compressible flow? Compressible flow is again a flow in which the density is considered constant. So if the density of fluid varies, sorry, okay. So incompressible flow is the flow in which the density is constant, whereas in compressible flow, the density of the fluid will vary from point to point. So this means in space. Okay. So for compressible flow, how you can write mathematically? Mathematically, the rho is a density here. So rho will not be equals to zero. So what will happen to incompressible flow? For this, the density will be, sorry, the density will be equals to zero, right? Okay. Next, we will talk about rotational flow and irrotational flow. So what is rotational flow? So the rotational flow is the flow in which the fluid particles, while flowing along the streamlines, okay, right, flow in which fluid particles while flowing along the streamlines also rotate about their own axis. Okay, so if there is any rotation of the fluid particles in the flow about their own axis, then we call that as rotational flow. So it can be like, let's say if there are some sediments or some impure particles or some other particles in the fluid, then what can happen? Then while traveling or while movement of the fluid particles, there can be some rotation about their own axis. Okay, so in that case, that flow will be called as rotational flow. Whereas if there is no rotation, then we call that as irrotational flow. Okay, here to just to note, here we have talked about one term called streamlines. Okay, what are streamlines? Streamlines are the lines that are tangent to the velocity field. So let's say if a fluid flow is happening, then if if we join the tangent line to the velocity field, we get the streamlines. Okay. 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 So we'll move to the next type. We have done with rotation. So next is laminar flow and turbulent flow. Okay, so what are laminar flow? Just to understand it visually, it is let's say so many water particles are moving in the same path, then we call that as laminar flow. Okay, and maybe I'll draw and then you'll understand. So let's say if the fluid flow is happening and all the layers of that fluid are moving parallelly, then we call this as the laminar flow. So if I write the definition, let's say, then a laminar flow can be written as, let's say, the type of flow in which the fluid particles will move well-defined paths. Okay, so let's say if any flow is there in which the fluid particles will move along a well-defined path, or we call this as streamlines, and all these paths, or let's say all these streamlines are straight and parallel, then we call this as the laminar flow. Okay, so what will happen in this kind of flow? The particles will move in laminars. Okay, so in this, what will happen? The particles move in laminas. What is laminas? Or laminas are, let's say, layers. So if the particles are moving in the layers, gliding smoothly over the adjacent layer. So let's say if this is layer 1, this is layer 2, this is layer 3, just to visualize. Then if all these particles are moving or are gliding towards uh, let's say, okay, for example, let's say if there are several fluid particles on this layer, layer 1, if this is moving on one adjacent layer, let's say layer 2, smoothly, then we call this as laminar flow. Okay, this is also called streamline flow. Okay, okay, and then yeah, what is turbulent flow? Anyone? So in this, how the water particles will move? So fluid particles moves in highly irregular circuitous path, or let's say we can easily write maybe in zigzag way. Okay, so let's say if this is the fluid layer, it can move something like this, and then this, and then somewhere this. Some, because of this kind of things, eddy can also form in the turbulent layer. Okay, so these are the eddies. There will be eddy formation in the turbulent flow. Okay, so turbulent flow can occur, let's say, when steep hydraulic gradient is existing. For example, let's say near pumped wells or rocks such as basalt or limestone, which contain large underground openings or cavities. There, turbulent flow is mostly seen. Or let's say if some hydraulic jump is there, we'll maybe we'll see that in the later slides. Okay, so now this laminar flow or turbulent flow is mostly measured, or let's say if you want to know, or you want to say the measure the type of flow, whether it is laminar flow or turbulent flow. Generally, there is one more type between this. We call that as transition fluid or transition flow. Okay, so for these, what we used Reynolds number. Okay, so we'll come to Reynolds number later. Maybe first we'll do some questions and then again we'll come back. Okay. Mm, okay, so we'll do some questions, right? Okay, so the question is, an ideal fluid is defined as the fluid which options are A is compressible, B is incompressible, C is incompressible as well as non-viscous, that is invisible, or D, that is has negligible surface tension. Anyone? If you have any guesses, you can put in the chat. B, okay. Okay, so here we are talking about ideal fluid. So what is ideal fluid? Ideal fluid is, if in the layman term we say, then ideal fluid is the fluid which we need for our analysis, in which everything we have made simpler, for example. Okay, so here ideal fluid will be the fluid in which we consider the density as constant. Okay, because if we consider density as variable, then what will happen that the process that we are involved, the process we are putting in, it will be more complex, and hence density should be constant. So with this we understand, okay, it should be incompressible, right? Then again we consider that viscosity, or maybe let's say we write with mu, the dynamic viscosity. We consider this as constant. So there is no viscosity. So if again if we consider that the fluid is viscous, then again the process becomes complex, and hence we don't consider it is in the ideal fluid. So here the correct answer will be is incompressible and non-viscous. So we consider that viscosity is constant throughout the fluid. Okay, so this is inviscid. Okay, is it clear? This is dynamic viscosity. Okay, so the correct answer is C. Okay. Okay, we'll move to the next question then. The next question is kinematic viscosity is defined as the product of. Okay, so just now we talked about dynamic viscosity, right? Okay, generally we see this using the Newton's law of viscosity, but okay, fine. So we have seen Reynolds number. Okay, for that I need to explain Reynolds number. Fine. I'll first explain Reynolds number and we'll come back here. Okay. Okay, so as I mentioned in the last explanation, right, that let's say if you want to understand the relative importance of viscous force in any fluid condition, then we use, let's say, Reynolds number. So generally in a Reynolds number you will see in some books it's written as N suffix R or R suffix C or maybe RE, something like that. Okay, so this Reynolds number, as I said, it is to express the relative importance of viscous force is in any flow condition, right? So mathematically we can write the Reynolds number as VL by nu. Okay, here V is the velocity of the fluid. Okay, then what is L? L is the characteristic length. Okay, so what is characteristic length? Generally, let's say if some passage is there, the width of that flow will be considered as the characteristic length here. For example, this Reynolds number we can use in open channel flow as well as in pipe flow also. So let's say for pipe flow, what will be the characteristic length? It will be the length of the diameter or the diameter of the pipe. Okay, if you consider a channel, then in that channel, the width of the flow will be considered as the characteristic length or L. Okay. Next we have nu. Nu is generally the kinematic viscosity. Okay, and this kinematic viscosity can be written as dynamic viscosity by density of the fluid. Okay, so somewhere you will see that Reynolds number is also written as rho VL by mu. Okay, here dynamic viscosity is mu, sorry, dynamic viscosity is mu and density is rho. That's how we can write this. Okay, so now as I said that Reynolds number, if you just go through the definition, then Reynolds number is what? Can you tell me? Reynolds number here, it is saying that it is the relative importance of the viscous force in any flow condition. So in this, what is happening? Two things are happening. One is the flow, and second, that there will be some viscous force. So Reynolds number will give you a measure of the uh, flow force. So what force will be the majorly there in the fluid or the flow? If something is moving, then what kind of forces it will exert? It will have the inertia force, right? So Reynolds number is the ratio of inertia force to viscous force. Okay, I hope the definition is clear, because we should not only remember the mathematical equation or something, we should also understand what physically those numbers mean, or what physically whatever equations we are seeing means. Okay, fine. Okay, now as I said in the beginning, that Reynolds number is used to tell you or used to denote what kind of flow we have, whether it is laminar flow, whether it is transient flow or transient or turbulent flow, or whether it is transition flow. Okay, transition between from laminar to turbulent. Okay, so generally, let's say if you consider pipe flow case, okay, case one I will write pipe flow case. So in case of pipe flow, what will be L? The characteristic length, as I said, it will be the diameter of the pipe. Okay, so if the Reynolds number is greater than 2000, then we call that as, oh, sorry, if Reynolds number, wait a minute, sorry. Okay, so if the Reynolds number is less than 2000, we call that as laminar flow. If the Reynolds number is greater than 2000, there will be transition from laminar to turbulent, and as much as I remember, maybe uh, greater than 2000 and less than 6000. So if it is greater than 6000, we call that as turbulent. Okay, I'll just check this value later, maybe it might be a little difference might be there in some books. Okay, and next we'll move to our case. Case 2 is flow through porous media. We are talking about porous media, right? Whenever we talk about the groundwater, we talk about porous media, because in this medium only we will have pores, so that we call as porous media. So in this case, if the Reynolds number is less than 1, or maybe from 1 to 10 sometimes we say, we call that as laminar flow. Okay, and if the Reynolds number is greater than 10, we call that as turbulent flow. Okay, so here, let's say in case of porous media, we will consider the apparent velocity. Okay, for the kinematic viscosity whenever we are calculating, and the average diameter of the particles of rock, for example, let's say sand grains, will be used for L. So the characteristic length, that is L, in the case of flow through porous media, will be considered as the average diameter of the particles of the rock. So let's say if one layer you consider, in that whatever rocks we have, the average diameter of all the particles, we consider that as the characteristic length. Okay, so turbulence will occur when the Reynolds number is more than 100, I guess. So more than about 100. But let's say if you talk about Darcy's law, okay, if Darcy's law, if you want to see whether Darcy's law is valid or not, so Darcy's law is valid only till Reynolds number less than 10. Okay, so we'll only focus till Reynolds number less than 10. So however, in any, let's say, many of the groundwater flow condition, you will see that Reynolds number is even less than 1. Not here we are saying that Darcy's law is valid less than Reynolds number less than 10. However, in most of the groundwater flow, you will see that Reynolds number is even less than 1. Okay, except let's say if there is heavy pumping somewhere, in that case the Reynolds number will increase from now. Okay, so and we also know that in the last class we have seen that Darcy's law is only valid for laminar flow. Okay, fine. Till this it is clear, right? And we'll move to the question. Okay, move to the question then. Okay, so so the question was dynamic viscosity is defined as the product of. Just now we have seen, right? Can you tell me the answer? Dynamic viscosity is written as the ratio of dynamic viscosity to the density. So the correct answer would be B. It is dynamic viscosity, correct. Dynamic viscosity by density. Okay. Okay. So the next question is the necessary condition for the flow to be steady is that. So just now we have understood all these things. What is a steady flow? Steady flow is the flow in which the characteristic, for example, velocity, pressure, temperature, etc., will be. Uh, I'll give you ways to answer, then I'll answer. So we discussed, right, that if we consider one single point in the fluid flow and if the velocity does not change with respect to time, then we will call that as steady flow. So the correct answer in this will be B. Here you see the velocity is constant. This means it does not change at a point with respect to time. So this one will be the answer. So if you consider the option C, that is the velocity changes at a point with respect to time, we call that as unsteady flow, right? Okay, so the correct answer is B. Okay, fine. We'll move to the next question then. Okay, so the next question is the necessary condition for the fluid or for the flow to be uniform is that. I'll give you as to answer. One? No? Okay. So uniform, we have seen the characteristics will be constant with respect to the space, right? So here, which one is D? None of the above. Let's see. Yeah, you see the option B. Here you see the velocity is constant in the flow field. In the flow field, as in the whole space. So let's say if the fluid is starting there, its flow from here and it is ending till here. Okay, then the whole thing we call as flow field. Okay, so in the whole space, if the characteristics or let's say the velocity with respect to space is zero, that is what B is saying. The velocity is constant in the flow field with respect to time. Okay, so this means that time is the constant here, whereas in flow field it is not changing. So the correct answer will be B. Okay. Okay, we'll move to the next question then. Okay, so the next question is a flow is said to be laminar when your options are the flow particles move in a zigzag way. Number two, the Reynolds number is very high. Number C, the fluid particles moves in layer parallel to the boundary. And number D, none of the above. This one is simple like this. We have seen that a flow is said to be laminar when it flows or the fluid particles moves in laminars, or as I said that layers which are parallel to the boundary, we say that as the laminar flow. So the correct answer would be C. Okay, yeah, the option here is wrong. It will be C, okay? Because the fluid particles which moves in a zigzag way, we call that as turbulent flow, right? If the Reynolds number is high, we call that also as turbulent flow. Okay, so the correct answer is C. Okay, we'll move to the next question. Yeah, it is easy. Reynolds number is defined as the ratio of, options are the ratio of inertia force to gravity force. Option B, ratio of viscous force to gravity force. Option C is ratio of viscous force to elastic force, and option D is ratio of inertia force to viscous force. Just now we have discussed, right, that what is Reynolds number? It will express the uh, like how much relative importance it has or the viscous flow has with respect to the flow. So flow has inertia force, whereas viscosity will have viscous force. So the correct answer will be inertia force to viscous force. That is option D. Okay, so the correct answer will be D. Fine. Okay, so the next question is Reynolds number is mathematically expressed as, just now we have seen, right? Can you answer this? This is easy. I will stop for a moment so that you can check all the options. Anyone? Have seen, right? Maybe I'll show you before where I explained. Yeah. Here we see that the Reynolds number. Not sure if we're able to see this or not. Yeah, I think now I'll see. Okay. So here you can see that Reynolds number is written as rho VL by mu. Okay, where rho is the density, V is the velocity of the fluid, L is the characteristic length, and mu is the dynamic viscosity. Okay. Okay. So with this, we move to the question. What is the question? Can you now answer this? Correct answer would be C, right? Okay. Okay, so we'll move to the next explanation now. So we have seen that Reynolds number is valid or Reynolds number is low when the flow is laminar, right? And we also discussed that Darcy's law is valid only for laminar flow, right? So let's say if there are the speed of the fluid is very high, okay, at the upper end of the laminar fluid, let's say. So at higher speeds, what will happen? We know at higher speeds, the flow rate, that is Q, let's say, will become proportional, but proportional, not to the head difference. Okay, because in the Darcy's law we saw and we told that Darcy's law is valid for laminar flow, right? And we know from Darcy's law Q can be written as K into A into dH or dH by L, for example. Here dH is nothing but the head difference, right? We have discussed this earlier in the last session. Okay, so here we see that Q is proportional to the head difference, right? Whereas this is only applicable for laminar flow. If there is higher speed, that is turbulence is there, then the flow rate will become proportional but not to the head difference, but to the square root of head difference. Okay, so mathematically how we can write it is as Q is proportional to root H or root DH, whatever you say. Okay, so although let's say that Darcy's law is applicable to most of the flows of groundwater, whichever is found in nature, the higher flow speed that occur immediately around, let's say, uh, it will result in head losses which increase in the square relationship. Okay, so we can write that from this q equals to, for example, some constant I'll write, maybe m I'll write to reduce confusion. So we can write q is m into root h, that is q square is, again let's see, if I write constant as m1, then m1 into h. Okay, fine. Okay, so with this we'll have one question now. Is it clear till here? Okay, I'll consider that it is clear. So we'll move to the next question. Okay. Okay, so the next question is, at higher flow speed, if the well discharge is doubled, then the head loss will be what? Just now we have discussed, with that only you can answer. We have just seen that sorry, at higher flow speed we can write q equals to maybe m1 into, sorry, m1 into h, right? So here we are saying if the well discharge is doubled, then the head loss will be what? Okay, so we can write, let's say, q1 equals to m1 into h1. Okay, that is when the q is not doubled. Now if the q2 is double, that is 2 into q1, then what will happen? We can write q2 as m1 into h2, right? Or head difference. Then you can write this as 2q1 equals m1 into h2. You see here what is happening to head here. Wait a minute. Sorry, it should be q square, right? Just now we have seen. Yeah, q square is 1 into h, right? So we can write q1 square equals to m1 into h, and q2, sorry, q2 is given as 2q1. So we can write q2 square equals to m1 into h2 square. That is 2q1 square is m1 into h2. So m1 into h2 is written as 4 into q1 square. That is equals to 4 into m1 into h1, right? So we can write this as q2 is 4 into q1. Oh, sorry, h1, h2 as 4 into h1, right? We just cancel out m1 and we can write the new head loss as 4 times the h1. So the correct answer will be increased by 4 times. Okay, I hope this is clear, right? So this means what? If the well discharge Q is doubled, the head loss over this part of the flow path must be increased by 4 times. Okay. Okay. So this only will explain the yield depletion curves. So let's say, okay, I'll come to this in the next slide. Fine. Okay. So the next question is, a useful way of assessing the behavior of the well is to pump the well at a different rates and measure the drawdown at each rate by what? Okay, so just now we have seen, right, that in this only we will see that if there is higher flow, then the Q will be discharge will be doubled when and discharge is doubled, then the head loss will again become 4 times. So these things, whatever we have studied about laminar flow and the turbulent flow, okay, maybe explain that in later slide. So this will explain why the yield depression curve shows a drawdown. So let's say if we consider one ground surface, this is the ground surface, for example, okay, and then we have a pumping well, okay. Sorry. So let's say if this is the water table, and somewhere here is the aquifer, and below this, let's say we have some impervious layer. Okay, so when pumping will happen, let's say Q, then what will happen? There will be a drawdown into the water level. So the water will become somewhere like this, because water will flow something like this, right, from all the directions, and hence the water table which was here, it will go somewhere deeper because of the pumping that is happening. Okay, and this is mostly given by yield depredation, sorry, yield depredation curve. Okay, which will show the drawdown that increases faster than the well discharge. Okay, so it will this yield depression curve will explain what? It will explain, let's say, why any designer of the well should keep the speed of the water as optimum as possible. Okay, because let's say if you are keep pumping the well or keep taking out the water from the well as at a continuous rate, what will happen? Here, this drawdown will keep happening, and the drawdown will become more steeper, right? And hence you should keep the discharge at an optimum rate so that the drawdown won't become steeper, such that it might be possible at some times that you are keep continuing pumping, and hence at sometimes you will see that there is no water coming out. However, there are water in the subsurface. That is just because the pumping rate is very high. Okay, so you should keep the pumping optimum, and also you should keep some lag time between pumping hours. So let's say if you do pumping for 30 minutes, you should wait for some time, or maybe some depends on the geologic condition and so on. Okay, okay, fine. So here we discussed about three terms. First one was drawdown, right? What was drawdown? So drawdown is like the distance between the pumping water level and the static or rest water level. We call that as drawdown. So here, if this is the rest water level, and here we have the new water level, this length we call head loss, right? And this head loss, because of this head loss, the water table has moved, or this dashed line which you can see. So this we call as drawdown. Okay, then we also talk about aquifer loss. What is aquifer loss? So the part of the drawdown that result from water flowing through the aquifer to the well. Here you see from the aquifer also water is flowing to the well. So there is a loss from the aquifer. So we call that as the aquifer loss. And then we also have well loss. What is well loss? The part of water that actually flow into the well across the well face. So what can happen from this part also, from this well face, the water can seep through, right? And then it can again join the water table. So we call that as well loss. Okay, so these head losses are important. Why? Because let's say in order to lift the water to the ground surface, the pump must impart some energy to the water, right? Because we generally, you will see, you will use the mechanical energy or maybe electrical energy to pump the water, right? So we need some energy to pump the water, and hence we should know all these kind of head losses. So if the drawdown is more, what will happen? If the drawdown is more, then more energy is required, right? Okay, therefore it is, as I said, it is essential to provide some amount of time so that well should be as efficient as possible. Okay, so generally we use the yield depredation curve, as I said. Okay, in y-axis we will have the drawdown, and in x-axis we will have the yield. Okay, and it will be somewhere curved. Okay, so this is the yield depression curve. So the useful way of assessing the behavior of a well is to pump the well at different rates so that we can know at what optimum rate we can pump the well. Okay, and we measure the drawdown at each rate. So now if you just see for ideal case, then this is for the Darcy's law. Okay, so this is what yield versus drawdown curve we have. Okay, so in this we talk about something called specific capacity. Okay, specific capacity is generally an index to understand transmissivity. We have talked about transmissivity before in the earlier slides. We write T is equals to KB, right? Remember, for confined aquifers and so on. Okay, So it also serves as a parameter of yielding capacity of aquifer well. So it will give you how much of water you can extract of aquifers of wells. Okay. So generally there is something called yield factor. Okay, generally designer will consider this yield factor to design how much optimum, at what optimum rate the pumping should happen. Okay, and this yield factor is given as the ratio of specific capacity to the aquifer thickness which is screened. Okay, so in let's say in confined aquifer, let's say the pumping water level is above the top of the aquifer. Okay, then what will happen? The yield depredation curve should be in theory. For example, in theory, if you in ideal condition you consider, then it should be a straight line, as we can see for the Darcy's law. So that is, flow is proportional to the hydraulic gradient. However, generally if you see in the natural case and all, the relationship is more likely to be a curve. Okay. Okay, so with this I hope you have understood everything. So with that we'll move to the question then. Okay, so the question is, a useful way of assessing the behavior of a well is to pump the well at different rates and measure the drawdown, and each rate is by option A is yield drawdown curve, option B is groundwater level storage curve, option C is intensity duration frequency curve, option D is none of that. Just now we have discussed, right? So the correct answer is yield drawdown curve. Okay, hope this is clear till now. Okay, we'll move to the next section. Okay, this might be the question from previous things. We have seen the process of precipitation which replenishes the groundwater supply is known as. So we have precipitation, we know what is precipitation. Now using that precipitation, the groundwater supply is getting replenished. This means more water is getting added into the groundwater. This process is called as, we know this, right? This process is called as recharge. Okay, so the correct answer is A. Okay. Okay, so we'll move to the next question. If the groundwater is moving radially away from an area, okay, so before that maybe I have something to discuss. Okay, one type of flow which we left was, I think 6 or 7 it was. We have not discussed about one-dimensional, two-dimensional, and three-dimensional flow. Okay, so let's say if a flow is happening on, let's say if this is the line that you can see, if the flow is happening only in this dimension, we call that as one-dimensional flow. That means the flow in which the flow parameter, for example, the velocity, is a function of time, and it's a function of, okay, I'll write it as one only. So velocity is a function of time and one space coordinate only. So maybe 1d, that is maybe let's say in only in x-axis. Okay, so if the velocity or any characteristics is a function of time as well as x coordinate only, then we call that as one-dimensional flow. Okay, similarly, if the velocity is maybe let's say in which velocity is a function of time as well as all three mutually perpendicular directions. So let's say if you consider three dimensions and the flow can move anywhere in this space, we call that as three-dimensional flow. So the velocity for this, velocity for three-dimensional flow will be written as, let's say if u is the velocity component in the x direction, then it can be written as f1 of xyz and time. Okay, v, which is let's say velocity in the y direction, it can be written as some other function of xyz and t, and w will be written as some other function of xyz and t. Okay, so for let's say if you consider 3D flow, in case of 3D flow, let's say if you call up the specific discharge, we have seen what is specific discharge, right? Specific discharge Q, we know that is equals to capital Q by A, where Q is the flow rate and A is the cross sectional area. So we can write this Q in three dimension, that is qx I cap plus qy j cap plus qz k cap. Okay, so in all three directions there will be what? There will be specific discharge, that is qx, qy and qz. Okay, so generally qx, qy, qz we are seeing in Cartesian system. You can see in any other system also. So if the formation is homogeneous and isotropic, we know what is homogeneous and isotropic, right? So if the formation is homogeneous and isotropic and groundwater is of, let's say, incompressible flow is there, and inviscid it is. So we are considering one ideal flow. So in ideal flow, we'll have the layer as homogeneous and isotropic. Then it should be incompressible flow, it should be inviscid flow, and so on. So the components of this specific discharge will be given using Darcy's law. So if that is the case, we can write Qx as minus Kx into del h del x, where del h is again the head difference and dx is in the in x direction. Whereas if you write qy, it will be ky into del h del y, and qz will be written as minus kz into del h del z, right? So, but this is an ideal case, okay, for ideal aquifer, ideal flow. Okay. Generally, if you see the rocks and all are non-homogeneous and anisotropic, and therefore this Qx, Qy, and Qz will vary. Okay. Okay. So we'll move to the next question, but okay, for this also we need something. Okay. Okay. So are now we have now discussed all types of flow, then how it moves and all. Next, we'll move to the direction of groundwater movement. So understanding in which direction the groundwater is moving is very essential. Why? So that we can know that where the head loss will be more, where the head loss will be less, and so on. There are several applications in which we need the direction of the groundwater movement. Okay, so groundwater, we know how it moves. What is the basic principle? The basic principle is that movement will be from high head, or let's say high potential, to low head, right? So high potential to low potential, right? So now if we know where the water is flowing at what depth, then we can also create contour lines on water table, right? So let's say if you just see the top view, it can be possible that somewhere, let's say here, we have something like this. Water table is at, let's say, 1 meter. Okay, if you go far, then water table is at 2 meter. Okay, somewhere like this is maybe 3 meter, and so on. Okay, so we can create contours of the water table, right? So we call this, we have known that the contour lines on the water table and piezometric surface maps, we can connect all the equal heads, right? And then movement of the groundwater will be perpendicular to these lines, right? So if you see, the movement should be somewhere in this way. So the direction, this one is the direction of flow, right? So with this concept only, we create the flow net. What is flow net? Flow net is a network, okay, in which we'll draw both flow lines and equipotential lines. Okay, what is flow lines? We have talked about streamlines, right? Kind of that only. So flow lines is the line in which the flow will occur. Okay, whereas equipotential lines are the lines in which there will be equal heads. Okay, so that's why we call it as equipotential lines. This means equal potential, that is equal heads. So if we join the all the points having equal potential or equal head, we call that line as equipotential line. Okay, so therefore these flow lines and equipotential line will always be perpendicular to each other. Okay, so this equipotential line we generally get through how much head we have at which location. Okay, so but we also see that in many areas it is not possible to obtain sufficient data to construct this kind of water table or piezometric surface maps. Okay, so let's say if what we do generally let's say if you consider three wells, you see three wells somewhere. Okay, and now we know that okay, here the water table is somewhere 27.5. Okay, here maybe it is somewhere near 27.0. Okay, and this well, so these three are the observations that you have. Let's say well A, well B, and well C. For well A, you know the water level it is at 27.6. Okay, for this you know that the water level is at somewhere 26.8. For this, let's say for example 27.2. Then what you will do, you will join all these three wells or wherever the observations is there. Okay, and you know that flow lines will always be perpendicular to the equipotential line. Sorry. So whatever line this you can see 27.5, 27, these are all heads, right? So the flow will always be perpendicular to this line, and hence in this case the direction of flow will be this. Okay. Okay. Okay, so the general direction of groundwater movement in such areas, now we saw that it can be determined if measurements can be made in three wells. For example, let's say ABC. So how to solve and all, it is simple, it is not that difficult. We might discuss in the next sessions and all. So what we do, we generally use the 3-point problems to solve this direction of problem. Uh, so the problem of direction of the flow. Okay, so we can also determine the movement of groundwater radially away from an area. So let's say here we see that the flow lines are somewhere like this. Okay, flow is moving somewhere like this. Then what does this mean? That if there is a well here, for example here, okay, maybe so if there is a well in between, then and if we are seeing that the flow lines are going radially outward, this means what? That the water is moving in this direction, in the flow line direction, and hence this water in this well is recharging the subsurface layer, and hence we understand that using these flow lines we can understand if the flow or the movement of water is radially away from an area in all directions, that indicates that this one is, let's say, recharge well, because it is recharging the subsurface, right? Whereas let's say for example we'll consider, let's say this is a well, okay, and you see that the flow is coming in this direction from all the directions, then this means what? It might be possible that we are pumping the water from the well, right? If we are pumping, then what will happen? All the water from all the sides, as we saw in the cone of depression, all the water will come into the well, and hence the flow lines will be will be how it will be, it will converge to this well, right? So it can be an example of pumping well. So this means that discharge is happening. Okay, so if there is any discharge well, or if there is any pumping happening in the well, or for example let's say if stream is there, in stream mostly what will happen, the water will flow into the streams, right? And hence the streams can also be considered as a discharge point or discharge, let's say, length. Okay, so from by seeing the flow lines and equipotential lines, you can get the processes that is happening in that region. See how we understood whether recharge well is there or discharge well is there, or pumping is happening, or let's say stream is there, and so on. Okay, so with this you can understand that what kind of process is happening. So for that we generally you create this kind of flow net. Okay, so flow net, as I said, that both flow lines and equipotential lines are perpendicular to each other. However, in maybe the real case scenario, what will happen? These are not the aquifers are not homogeneous and isotropic and so on. And hence, if let's say if you see the flow lines, if the flow lines is somewhere, okay, maybe I'll make in the next slide. So let's say if this is the flow lines, for example, okay, then how the equipotential line should be something like this, right? let's say 2.5 meters, 3 meters, 3.5 meters, and so on. So these are the flow lines, whereas these are the equipotential lines, right? So what you can observe here, if there is an ideal case, then you see each of these boxes are kind of square, right? So if the selected flow lines are drawn on a water table, or let's say piezometric surface, then at approximately the same distance apart as the equipotential line. So let's say if the equipotential line are at 0.5 meter and the flow lines are drawn on the water table or the piezometric surface at 0.5 meter, then the spaces between them will become a square. However, due to let's say geological formation or different kind of geological characteristics or fluid characteristics, it will change. And if let's say no water is being added to or withdrawn from the aquifer in the area, the amount of water moving through different squares is equal throughout the area, right? However, as I said, that this is an ideal case. Differences in spacing are caused by differences in permeability or thickness of the aquifer. So what is flow net? Flow net is a graphical representation. Here we are seeing in two-dimensional steady state groundwater flow through aquifer. Okay, steady state groundwater flow. Okay, through the aquifer. So that is what flow net is. Okay, okay, and how to construct the flow nets and all. We are not discussing in this lecture. Maybe we can see, we will do in the next lectures or maybe something like that. Fine. Till this, everything is clear. Okay, so we'll move. Wait a minute. Everything is there, right? Yeah, okay. You guys can hear me, right? Okay, fine. There was some network connection issue. Fine. Okay, yeah. So we'll move to the question. The question is, if the groundwater, I will maybe here I make this so that you can understand that these two are different. Okay. The question is, if the groundwater is moving radially away from an area in all direction, it might indicate, your options are discharge well, uh, yeah. So your options are discharge well, a stream, recharge well, or option D is pumping well. So as we are seeing just now, we saw that if the groundwater is moving radially away from an area, this means that that well is recharging the subsurface, and hence the correct answer for this will be C, that is recharge well. Okay. Okay. So the next question is, what is the minimum number of observation wells required to determine the direction of groundwater flow? Okay. And just now we saw that the minimum number of observation wells that is required to direction of the groundwater flow is 3, right? So the correct answer will be D, that is 3. Okay. In the flow net, we saw, what was the question? The question is, flow lines and equipotential lines are whether they are parallel to each other. Option B is perpendicular to each other. Option C is independent of each other. Option D is at any angle to each other. I hope that is. It's working. Okay, so the correct answer is that flow lines and equipotential lines are perpendicular to each other, right? That's what we have seen. So the correct answer is B, that is perpendicular to each other. Okay, we'll move to the next question then. Okay, the next question is, the unit of intrinsic permeability is. We have seen this in the last session also, right? So the unit of intrinsic permeability is centimeter square or area square, area units, that is centimeter square here. So the correct answer is option D. Okay. The next question is runoff is measured in. We have seen that runoff is generally measured in meter cube per second, right? So the correct answer is B. Okay. The next question is choose the correct equation from the following. We know, okay. So your options are runoff equals surface runoff plus groundwater flow, or surface runoff minus groundwater flow, surface runoff divided by groundwater flow, or surface runoff multiplied by groundwater flow. So we know the correct answer will be surface runoff plus groundwater runoff, or the base flow. Can write this as base flow also, right? Okay. So the correct answer is E. Okay. The next question is changes in the spacing of water table contours can be due to changes in. Your options are flow rate, hydraulic conductivity, aquifer thickness, or all of the above. We know change in the spacing of water table means what? This means the change in the hydraulic gradient. Okay. So here the question is change in the hydraulic gradient or contours can be due to the change in. So we know if the flow rate is changing, if the flow rate will change, then obviously the hydraulic gradient will change, and hence the spacing of the water table contours will change. If hydraulic conductivity will change, then also the hydraulic gradient will change. If the aquifer thickness is changing, because we know from the Darcy's law we can write Q equals to minus K into A into H by L, right? So here we can write this as the hydraulic gradient, right? So we can write Q equals to minus K. A you can write as, let's say, B into W, where B is the thickness and W is the width. I'll write B is the thickness, W is the width into I. So here you need to understand whether this is what we are looking for. So change in the hydraulic gradient. If the flow is changing, then the I will change. If the thickness is changing, then the I will change, right? If this hydraulic conductivity, this is hydraulic conductivity, right? If the hydraulic conductivity is changing, again the I will change, right? So the change in the hydraulic gradient will depend on all of the above. It is flow rate, hydraulic conductivity, and as well as aquifer thickness. Okay. So the correct answer is D. Okay. So the next question is in a homogeneous isotropic confined aquifer, continuous pumping from a well produces a cone of drawdown. That is what we saw. What is the approximate shape of the drawdown surface under the steady state radial flow? We have seen this, right? Can you please answer? We have seen, right? Let's see if this is the down surface, and somewhere here is the water table, and somewhere you consider one fully penetrated well, and here somewhere, let's say, some aquifer we are considering. Okay, this is impervious layer, and there is some pumping happening. Here is pumping. Okay, so now in this case, if pumping is happening, what will happen? The flow we saw will come somewhere near like this, right? So what kind of formation we are having? Some conical shape we'll have, but in three-dimensional space. Okay, so there won't be a flat surface extending uniformly in one direction. It won't go just, let's say, a plane. If you are considering, it won't go like that. Okay, so it will go like a conical surface with drawdown increasing toward the pumping well. So we saw if just near the pumping well we have a very steep drawdown, whereas if you move forward or if you move very far from the well, then it will be near the water table. Okay, and that's how a conical surface with drawdown increasing towards the pumping well comes. Okay, so the correct answer for this will be option B. That is, in, let's say, homogeneous isotropic confined aquifer, if there is a continuous pumping which is happening from a well, it will produce a cone of drawdown which will be of shape or surface will be like conical surface with drawdown increasing towards the pumping well, right? Okay, we'll move to the next question. The next question is the efficiency of the well for abstracting groundwater can be written as. So we know we write the efficiency of the well for abstracting groundwater as the ratio of aquifer loss to the total drawdown. We have discussed about what is aquifer loss, what is drawdown, and what is well loss some time back, right? So the efficiency of the well for abstracting groundwater will be written as the ratio of aquifer loss to the drawdown. Yeah, just now we have seen. Okay, so the correct answer for this is aquifer loss to total drawdown, right? So as I mentioned, what was drawdown again? If we just want to clarify, what is drawdown? We have discussed this, right? So the head loss that we were talking about, right? So the head loss, or let's say the distance between the pumping water level and the static or rest water level, we have seen earlier. Maybe we can see here also. Okay, so here, where is the head loss? Let's say the water level has dropped from this to this. We see this as head loss, that is HL. Okay, now this head loss is because of the pumping happening, right? So the distance between the pumping water level and the static, or let's say the rest water level, is called as drawdown. Okay, and aquifer loss was what? Aquifer loss was in this only, in this drawdown. Whatever water is flowing through aquifer to the well, we call that as aquifer loss, because water is losing from the aquifer. So we call that as aquifer loss. We also talked about well loss, right? What was well loss? That let's say from the well face only, there can be some seepage. Okay, so in that case, whatever loss is happening from well, we call that as well loss. So the part of the water that actually flow into the well across the well face, we call that as well loss. So generally what we do, we put some screens kind of thing. So in the periphery of the well, we put some kind of screens or some kind of pipes, but it will be uh, somewhere like this. So let's say if you consider a pipe, or which we are putting in the well, there will be small perforations like this. Linings will be there, so that the water can flow inside or outside, right? So these are perforations, we can say. Okay, or lining, maybe line spacing, not line spacing, maybe perforations, we can say. So it is kind of some gaps is there in each of these pipes, so that there won't be erosion from the well side, but the water will flow properly. Okay, so these kind of things will be here. Okay, we call this as slotted lining tube. The whole tube is called slotted lining tube. Okay, fine. So we saw the efficiency as this, right? Any questions still here? I think this one was the last question. Yeah. Yeah. So this is the last question we have. Any other questions or any doubts you have in today's session or in the week 4 lectures? Anything? Okay. If not, we'll stop it here. If you have any questions, you can write to me, or maybe we can discuss in the next session. I hope the assignment questions are not a big problem here. I saw the assignment questions are much easier on, right? Okay. So with that, we'll stop then. Any questions? Okay. If not, then we will stop here. Thank you so much.